Hi everyone, my name is Raquel Ortaza and I'm the Chief Scientist at UberATG, as well as a professor at the University of Toronto. Today, I will be talking about localization for self-driving vehicles. Self-driving vehicles are one of the most complex and safety-critical modern-day applications of robotics. Leveraging rich maps can enhance performance and safety in areas such as perception, active prediction, and motion planning. In order to leverage these maps, the vehicle must know its position within them. This is the task of localization. Self-driving vehicles utilize high-definition maps, which contain both detailed geometry and semantic information about the environment. These are used for precise localization of the self-driving vehicle as prior knowledge for the autonomy system and for simulation. Self-driving companies are interested in creating globally consistent 3D maps of the world. In the industry, many passes over the same area are required for these maps to be complete. However, we would like to reduce this requirement as this is very expensive. Furthermore, maps typically require large amounts of memory to be stored, preventing them from being able to produce and use at scale. Finally, we would like the maps to only contain permanent elements that we will see every time we drive around the map area. Building geometric maps is typically a three-step process, where the data is first collected by a fleet of vehicles. Map building is typically done from multiple passes through the same area to ensure full coverage and to be robust to transient objects. Then the data is offloaded and the problem is decomposed into trajectory fitting of small chunks, which can be performed in parallel. This is then combined into a massive global optimization problem, which can be solved, for example, with graph slam techniques. The result is high-fidelity maps of our cities. In the video, you can see reconstructions using both LIDAR as well as cameras, which are very complementary sensors for this task. In the reconstruction I just showed, we have removed potentially dynamic objects, which are, for example, moving or parked cars, by exploiting a state-of-the-art semantic segmentation. This state-of-the-art technique is illustrated in the video here. Filtering these dynamic objects is important and results in much crisper maps. This is illustrated in green versus red in the video you earlier just seen. HD maps contain also very rich semantic information. This includes the location of traffic lights, lanes, crosswalks, as well as the rules of traffic at each intersection and road segment. As illustrated here, these maps are extremely complex and a great prior for the autonomy system. These semantic layers are typically manually annotated with very little automation. A process extremely tedious, time-consuming, and expensive. If you are interested in knowing how to automate this process, check out our tutorial on self-driving. The goal of localization is to, given a sensor observation and a preview map, infer the location of the car in the map. We focus explicitly on map-based localization, that is localization within prior maps, since this is necessary in order to leverage the HD maps described in the previous section, in order to achieve maximum safety. Formally, we wish to model the robot's belief over the state space, where for localization, the state space corresponds to the robot's pose in the world. We denote the pose of the current time by xt, and the observations by z, and m denotes the prior map. The Global Navigation Satellite System, GNSS, is a common source of input, which is often involved in computing initial pose estimates, which are then refined with other sensors, such as cameras and LIDAR. Over the last 3 decades, cameras and LIDAR have been leveraged in a wide variety of localization algorithms, many of which will be discussed later. IMUs and wheel encoders are also leveraged as additional cues, as they provide information that is complementary to the observations from cameras and LIDARs. There is a wide range of representations which can be used for localization, in terms of localization maps. HD maps can be built and annotated with information such as lane boundaries, lane types, signs, etc. These kinds of maps can also be used for localization. 3D geometrical models can also be employed. These models can be represented as dense or sparse point clouds, surface, or other kinds of 3D primitives. Topological maps are possibly non-metric graph-like representations, such as those found on OpenStreetMaps, OSM for short. They are typically much less detailed than the semantic maps described on the left. Finally, simple occupancy maps can also be used. They are often represented simply as a top-down view of the world. Such maps can also contain additional attributes, such as surface reflectance or color, and have the advantage of encoding rich information about the structure of the world, while also being easier to store than other representations. The main characteristics we would like from a self-localization system running at the scales are low cost, as we naturally want to map very large distances, the ability to localize in real time, high accuracy centimeter level localization, and robustness, the capacity to handle and recover from failures. However, in order to achieve these goals, there are still several major challenges which we have to overcome. Localization systems must be robust to the presence of dynamic objects in the scene, as these are irrelevant for localization. Geometrically degenerate areas which lack distinctive geometric cues, can also be problematic. These areas are challenging for geometric localizers since observations can't be uniquely aligned to the map. Sensor noise affects all sensors in different ways. Multipath effects can affect both GPS and LIDAR and cause difficulties localizing. Finally, environment changes such as construction mean that localizers must be able to adapt to cases where maps become updated. Now that we have gained some big picture context of what localization is trying to solve, it's time to dive into some of the mathematical foundations of probabilistic localization systems. There are two main parameterizations of vehicle pose using SDVs, short for self-driving vehicles. The minimal parameterization has just 3 degrees of freedom, the latitude, longitude, and the yaw of the vehicle with respect to the map. While very minimal, this representation makes sense for vehicles since they travel on the ground manifold, and the other 3 degrees of freedom, pitch, roll, and height, can be readily derived from the map. The full 6 degrees of freedom representation is more complete and fully describes the pose in the 3D world. It can lead to more robust state estimates, albeit at higher computational cost. It is also required in cases where the on-ground assumption no longer holds, as is the case, for example, in flying cars. Note that we do not only care about a point estimate of the localization, but also a confidence measure over the space. The probabilistic framework allows modeling of uncertainty as well as tracking multiple pose hypotheses and recovering from failures. We have thus established the benefits of modeling a probability distribution over the state space, rather than a point estimate, uncertainty modeling, multi-hypothesis tracking, and recovery from failure, to name the main ones. In this context, we can look at localization as a probabilistic inference problem, that is, estimating the belief over our state space, which in this case happens to be a position. Mathematically, we denote our states at time t as xt, and our observations, which can be LIDAR, IME, or GPS, using Z. We operate under the Markov assumption, where the belief over our state at time t-1 encodes all the information from the past states, allowing us to predict where we will be at time t. We will see why this is a good idea once we have a look at how this estimation is implemented in practice in the next few slides. Note that we restrict our scope to the case of online localization, which assumes a good initialization is always available to solve the problem. We will discuss global localization and system initialization later in the talk. Focusing on discretized temporal dimensions, for example, at 30 Hz, use localization as a recursive Bayesian filter, which can be solved with a simple yet effective algorithm. So right now, I'm going to give a very brief overview of how the Bayesian filtering framework works in the context of localization, but it's worth pointing out that this is a very general framework that is in no way restricted to the task of localization. There are essentially 2 main steps in the algorithm that keep getting repeated over and over as a robot moves through an environment. These are prediction and observation. Each iteration begins with the prediction step. This step uses a propagation model to compute a prior belief over the current state based on the current state based on the previous state posterior. For localization, this propagation model can be given by a kinematic model, for instance. Since I was here 0.1 seconds ago and my velocity is this is where I will likely be around, assuming if I assume constant velocity. The rightmost term in the last steps belief is the last steps belief, while the middle one highlighted in magenta represents the propagation model built into our system. The second step updates the prediction from the past step based on the current observation. This is what integrates new observations from our sensors into our belief. On the right, we see an illustration of a Bayesian filtering procedure. The state space is unidimensional. It's just a scalar depending on the robot's position in the corridor. The robot on top begins with no idea where it is. The belief over the state space corresponds to a uniform distribution. Then, in the second row, the robot performs its first observed step and notices that it's near a door. However, the pose is ambiguous since it cannot tell which door it is. The robot then moves, applying its transition model to approximately propagate its old belief based on how it moves. This represents the first step of the second iteration. This increases its uncertainty, as denoted by the widening peaks, as directive emotion readings are typically noisy. Finally, in the second step of the second iteration, the robot observes another door and fuses this information with its current belief. This additional information helps disambiguate the robot's pose, allowing it to converge to a mostly unimodal distribution over its location. Note that this example is purely conceptual, since in practice we cannot solve the integral in closed form. Proper Bayesian filtering results in an integral over the state space at the previous time step that is oftentimes intractable. So there are a number of common approximations used to tackle the problem in practice. For example, we can assume that the distribution is unimodal, transitions are linear, and both the noise of the beliefs are Gaussian. This results in a Kalman filter. We can also approximate the integral via Monte Carlo sampling. This is known as particle filter or importance sampler. The third alternative is to discretize the distribution, which results in a histogram filter, which is easier to work with, but can be computationally expensive. So to recap, we can elegantly model recursive Bayesian estimation using a pure mathematical form. In practice, we have to make some trade-offs in order to implement this in a real robot. A Kalman filter is able to produce convenient continuous closed-form estimates, but it is limited in its modeling power. Its unimodal nature means that it is unable to track multiple hypotheses. Particle filters can bypass some of these issues and approximate the quantities by sampling. However, the modes of the distribution can still collapse as the number of particles necessary to model the distribution grows as an exponential function of the number of dimensions of your state space, which can be quite large. Histogram filters can also represent arbitrary system models and arbitrary noise models without risking any sort of collapse, albeit at a much higher computational budget and with limited resolution. However, later on this talk, we will see how we can still leverage the best parts of histogram filters without a large computational cost. A common element in all localization efforts is the need to always integrate new observations. Observations can take in a wide range of forms, ranging from direct sensor readings like the IMU, all the way to a neural network that perceives the 3D scene from sensor readings. Let's look at different observation models. Real-time kinematic systems leverage differential GPS and inertial measurement units to estimate vehicle trajectories. Semantic matching tries to match cues extracted from sensor observations to maps which encode the prior locations of such cues. Geometric alignment infers the vehicle pose by rigidly aligning the perceived geometry to a non-3D map. Camera to LIDAR matching aims to leverage inexpensive cameras to localize against maps built from more expensive LIDAR, either using heuristics or learned feature matching. Place recognition has localization as an image or LIDAR retrieval task. Localization then consists in mapping the sensor rhythms to a previously seen and localized 1 news neighbor search. Finally, LIDAR reflectance matching compares the LIDAR intensity rhythms to the map at multiple candidate locations in order to find the correct pose. In principle, any of these approaches can work with any of the previously discussed frameworks. You can do semantic matchings via a timeline filter, a particle filter, or a histogram filter. You can filter GPS using particle filters, etc. I'm now gonna highlight a few observation models with some of the work that the lab have done in the past few years. Let's look at semantic matching. This approach leverages compact maps of a few kilobytes per kilometer, storing only semantic cues like lanes, signs, turns, and road type, all of which can be stored as vector maps. At runtime, the car must recognize these elements and match them against the vector map to localize. Unfortunately, due to the sparsity of the cues, these approaches cannot achieve centimeter level accuracy and struggle in areas where the detection is challenging. Examples of these approaches include Lost, which require an OSM or OpenStreetMap vector map, and our recent work which exploits lanes and signs for localizing on highways, which can actually automatically create these safety maps and then localize to them. Geometric alignment methods rely on aligning 3D sensor data to pre-build 3D HD maps. These methods can be very accurate, relying on well-established, conceptually simple methods that can be robust to outliers, such as the iterative closest point algorithm. The downside is that these methods require a good initialization for convergence, as registration is prone to local optima. Additionally, storing and building 3D geometric maps can be challenging and expensive. Despite these drawbacks, these approaches are very popular in the self-driving industry, probably the most popular across all of them. LIDAR reflectance matching. This approach builds a map using LIDAR intensity imagery and matches online observations from the 2D image using simple template matching operations such as cross-correlation. These methods can be much more robust than geometric ones, especially in mostly featureless environments. For example, if you're in the middle of the desert. The template matching itself can also be implemented in a very computationally efficient manner and achieve centimeter level accuracy. At the same time, just like the geometric alignment methods, reflectance matching methods require good initialization. They also have relatively high map storage costs. Through the 2.5D maps used by these approaches are typically much easier to compress than 3D ones, as we will soon see. These methods also require very precise LIDAR intensity calibration, which can limit their scalability due to the difficult nature of this procedure. As when you are working in the self-driving industry, you need to have the same map for a fleet of vehicles. Potentially, these vehicles might not have exactly the same calibration settings. Finally, these methods are typically limited to estimating only 3 degrees of freedom, being unable to directly infer the height of the vehicle. However, as discussed previously, the height, pitch, and roll of the vehicle can be inferred from the map, yielding a good solution. Despite these drawbacks, many self-driving companies exploit localization systems based on LIDAR intensity matching. Our recent work has addressed the need for intensity calibration by learning a deep invariant mapping for matching in an end-to-end manner. First, we pass the online LIDAR sweep and the map through separate, fully convolutional networks to compute corresponding embeddings. Following the histogram filtering framework, we then compute a matching score for every pose within a limited search range of our dead reckoning pose. The search range is our X, Y, and heading, so 3 degrees of freedom. This matching can be performed very efficiently in the Fourier domain with specialized Gödel kernels, yielding localization times that are real time. The matching therefore yields a 3D score volume, which corresponds to the observation probability in the Bayesian filtering framework that we have reviewed before. This motivates us to go one step further. We incorporate a neural network compression model within this network. To encode the input map to a compact binary code. Importantly, we only need to store the binary code on the card. The compression model is highlighted with the gray box. This compression model is made end-to-end learnable. In other words, learning will decide what information will keep and what to discard. Unlike prior compression work, it directly optimizes the trade-off between compression and localization accuracy, as opposed to the trade-off between compression and distortion commonly used in the general-purpose compression literature. So overall, in this work, we use learning to get robust and compact feature representations. And we use model-based knowledge to formulate the problem and integrate prior into the Bayesian filter. This is a technique that is extremely robust to any calibration issues, and I can achieve 3 centimeter error with millions of maps. As a result, we have reduced storage by 3 orders of magnitude with only a slight accuracy drop. And importantly, our approach is much more storage efficient and accurate than storing maps using standard lossy compression algorithms. Based on our computation, this compression allows storing a centimeter accurate localization map for the entire high-definition US road network in a single commodity hard drive. By combining machine learning with human knowledge of the world, we have made localization more scalable. The take-home message is that when designing data compression algorithms for robotic applications, we should exploit the fact that consumers are robots instead of humans, and our goal is to preserve downstream task performance. Here we show some qualitative results. On the left is our online LIDAR. In the middle is the map, and on the right is the localization result. Vehicle pose predicted by our method is in red, and ground truth is in green. Note that in these cases, we can see that our pose and ground truth pose are almost perfectly aligned. I will now talk about a different topic, which is global localization. The method that we have seen so far have been focused on online localization. The natural question is, how do we obtain our initial pose? And how do we recover when Bayesian filtering method fails? This task is known as global localization. The challenges here are, for example, that the same place can look very different due to factors such as weather, time of the day, season, dynamic objects, and so on and so forth. Another challenge is that obtaining good large-scale training data for this task remains difficult. There are 2 main approaches for this problem, post-regression and retrieval-based localization. Post-regression takes images or LIDAR point clouds as input and directly outputs the pose for the car. This method is extremely fast, yet there is a lot of evidence that these methods do not achieve good accuracy at CT scale. Retrieval-based methods, on the other hand, are slightly slower and have potentially large memory requirements because they have to store the entire observation dataset, but tend to be much more accurate in large geographic scales. We have investigated the retrieval approaches in the context of self-driving and designed a large-scale dataset and benchmark for this task.
We introduced PID30M, a dataset for large-scale localization tailored for self-driving applications. For scalable localization in a city setting, we would like a dataset to 1. Be diverse, 2. Cover an entire city, 3. Provide accurate localization ground truth. Our dataset satisfies these 3 criteria and does so at an unprecedented temporal and geographical scale. Our dataset includes images and LIDAR point clouds, each localized with accurate 6 degrees of freedom poses. We also carry a consumer-grade GPS sensor, which we can use to bootstrap localization. Our dataset also provides a set of labels that allow researchers to better understand the limitations of current localization algorithms. For example, we provide sun angle, season, temperature, precipitation, and semantic segmentation as a proxy for occlusion. With over 25,000 kilometers driven, 30 million images and LIDAR readings, and an area of 50 square kilometers collected over 1,300 trips, our dataset is between 10 and 100 times larger than previous datasets released to the community. PID30M provides a challenging benchmark for large-scale localization, particularly suited to autonomous driving. We plan to create an evaluation server for automatic benchmarking and for keeping track of the progress by the community. We hope that our dataset will help researchers develop new and exciting algorithms for this task.
We also did an in-depth benchmarking, comparing multiple approaches on our dataset. The main takeaway point from our experiments is that the strong architectures with simple pooling schemes show excellent performance on this task. In this plot, the x-axis goes from 0 to 1 meter, and the plot indicates what % of the queries are correctly localized within a certain distance. As you can see, GPS struggles to localize even 5% of the images within a meter, which is not good enough for autonomous driving. We benchmarked baselines that are commonly used in previous work, including BLAD, NetBLAD, and LensBLAD. And we noticed that they only localize about 50% of the queries within 1 meter. These methods rely on BLAD pooling, which has established itself as a strong baseline for many retrieval tasks. However, training a ResNet 50 with average pooling performs very well on this task, returning over 90% of the queries within 1 meter, and over 70% within half a meter. Another thing that we can do is, instead of searching for nearest neighbor in the entire database, use GPS as initialization, and then search only within an area of, for example, 20 meters around it. This consistently improves results for all methods, and improves also our ResNet as well. The previous results were all using images only, but we can do a very similar experiment with LIDAR. Obviously, the performance of GPS is the same. The methods that we benchmark here are PointNet with max pooling, PCAN, and PointNet-BLAD. These methods all process points individually, like PointNet, and rely on complex aggregation schemes at multiple levels. In contrast, we represent LIDAR in with a Versa view representation, which we also use for perception and prediction in our vehicles, and are thus able to treat the point cloud as an image, which we pass through a ResNet 50 with average pooling. We have found that this consistently outperforms other methods as well. We can also use GPS for initialization, which helps most methods. It is curious, however, that GPS can slightly hurt LIDAR retrieval on short distances. This is because sometimes GPS can be off by more than 20 meters, so that retrieval methods initialized with LIDAR cannot recover from bad GPS in that case. Here are some qualitative results of our method. Note that on the left, we show the query, and the first 3 results are retrieved using the image. The last 3 results are retrieved using LIDAR. In this particular example, we see that the image retrieval network finds the same place only 61 centimeters away, but under snow conditions. This means that the network has learned to be invariant to the weather in the scene. LIDAR also finds the same place, but does so with only 17 centimeters error. In this other example, we see the image network retrieving the same place at night. Methods such as NetBLAD, and LensBLAD find images that look similar but correspond to a different place. Once again, LIDAR is consistently more accurate. The final example is a query that does not have a lot of distinguishable visual features for the network to latch onto. Nevertheless, the network can retrieve the same place by finding the same building. Again, LIDAR does a better job, finding an example that is only 12 centimeters away. Some remaining challenges in global localization include using both images and LIDAR. In the example that we described, the network uses images and LIDAR, and we found that fusing information from both is actually really non-trivial. Exploring for generalization of these methods to multiple cities also remains an underexplored. For example, we would like to train on a city on the East Coast and be able to generalize to cities on the West Coast, or even across continents. We would also like to explore systems that do both global and continuous localization. Training these two things together remains challenging. Finally, state-of-the-art large-scale systems for approximate nearest neighbor search rely on data structures that are themselves learned. So jointly learning to localize globally and efficiently find nearest neighbors will be an interesting area of research as well. So to recap, we have first described localization with previewed maps. Then we introduced Bayesian filtering for continuous localization. Here we discuss Kalman filters, particle filters, and histogram filters. We then gave an overview of methods for map-based localization, and finally we discussed global localization and its challenges. Important future directions include reducing our reliance on high-definition maps, as these remain expensive to build and hard to get right. Finally, Bayesian filtering typically discretizes time. However, in real-life sensory inputs come continuously, and they are typically at different frame rates, each one of these sensors. So designing methods that explore this fact remains challenging and very interesting. Finally, since we are interested in self-driving, we have to remember that we have limited computational resources on board. So designing systems that can reuse computation to do localization and other tasks such as perception, prediction will be a very interesting idea. Thanks for your attention. This is all from me. Thank you.